So we have seen Yoneda lemma, which can be called the fundamental theorem of category theory, and now we are going to come back to categorical properties. We have seen two categorical properties. Yeah, what are they? Initial object and terminal object. Yeah, not co-initial object, just initial and terminal objects. Fine. So now we are going to look at some more such constructions. If you remember, at one point I explained that if you are talking about the category, then there is some thickness in the morphisms because the home sets are thicker, they contain more than one elements. Yeah, and then there is just the pre-order collection, yeah, that whether there are morphisms or not, and then pre-orders and groups I mentioned, like monoids, they can be thought of as building blocks. So groups have parallel morphisms. Yeah, so these parallel morphisms are going to be our first topic of discussion. So we are discussing now what are equalizers. Okay, so equalizers are just, let me describe everything diagrammatically. So we are given two objects and a parallel pair of arrows, yeah, F and G, and now we want to talk about a morphism. Yeah, let me call that morphism D, some morphism from D to A, let me call it H, such that FH is equal to GH. FH is equal to GH, and there should be universal such thing. So by this actually I am going to give you one more type of ways, one more way where you could generalize injective functions. Yeah, so I want some morphism H which will make this happen. FH is equal to GH. Now suppose we are working in sets. Can you tell me some such D that will always work? Yeah, yeah, singleton, if at all A is non-empty. If A is empty, then obviously F and G can't really be distinct. Yeah, it has to be the unique map, so at that point we don't worry. But if it is non-empty, then we have got, you map it to any singleton.
Or you can take D as empty. Then
Oh sorry, so singleton will not work actually, right? Because singleton, maybe that is precisely the point where F and G differ. So therefore we won't necessarily get FH is equal to GH. But you can always choose D to be empty set and H to be the empty function, and then the composition is just going to be the empty function. So those compositions do agree with each other. Now this is the idea that we want to do in a universal sense. So we will construct some E and some morphism E such that first property is that, yeah, that Fe is equal to Ge, and second property says that whenever Fh is equal to Gh, then there exists a unique arrow, let's say K, from D to E, such that the diagram commutes. So this one, there exists a unique arrow K such that this diagram commutes, which means Ek is equal to H. Okay, so this is the best possible solution to this problem. We posed a problem, we wanted to make sure FH is equal to GH, and what is the best possible such solution? Amongst all such possible solutions, you can see that this is the terminal one. This is the terminal solution. Yeah, because we are saying there exists a unique way of factoring through E. And because it's a terminal in some appropriate category, yeah, we'll make this precise today. So that property makes sure that equalizers are unique up to unique isomorphism. Okay. So these so the pair E comma E is called the equalizer, sorry, an equalizer of F and G. So something to note here, that we are not just saying that capital E, that object is the equalizer. We are saying that that object together with this morphism, without morphism objects are nothing. Okay. So you can even just say that this little e is the equalizer, but you can never say that capital E is the equalizer alone. Yeah, because when we talk about little e, then it automatically has a domain. Its codomain is just going to be A, which is already given to you in the form of that diagram. Okay, and such an equalizer is a terminal object in an appropriate category and hence any two equalizers are isomorphic in a unique way. Okay, so there is a unique isomorphism between any two equalizers. What do I mean by that? If E1 and E2 are two equalizers, then there is a unique isomorphism from E1 to E2 and from E2 to E1. Where is this uniqueness of the isomorphism coming from? From the existence, there exists unique. Yeah, that is what is forcing us to make this thing true. Yeah, because if you remember when we were talking about two terminal objects, what we saw, T1 and T2 are terminal, then there is a unique morphism from T2 to T1, there is a unique morphism from T1 to T2, and the compositions also satisfy the property. So the compositions, like the round compositions in both sides, they have to be equal to the identity. So here also the same argument works, and therefore, so thus we can talk about the equalizer of F and G. Okay, so from an equalizer to the equalizer, yeah, we are just making this journey because it's unique up to unique isomorphism. Articles are important while writing English, but here also, like in mathematics, they have lot of meaning. Okay, so let's look at some simple examples. So in sets, what can we say? If A and B are two parallel arrows, what is E? All such things which make F and G equal after composition. X in A such that Fx equals Gx. Correct. X in A such that Fx is equal to Gx, and little e is the injection, is the inclusion in A, right? So this is correct. Now this shouldn't be a surprise actually if I say that this little e is always going to be a monomorphism. Very beautiful proof of diagram chasing. Yeah, that is what makes sure that these equalizers are unique. So, monomorphisms. If EE is an equalizer, then E is a monomorphism. Remind me, what is the definition of a monomorphism? If FH is equal to GH, no. FH equal to GH, that's not the definition. At least use the notations that we are doing. So let's say K1 and K2 are two morphisms. Okay, when is E going to be a monomorphism? Yeah, so suppose EK1 is equal to EK2. Yeah, we need to show that K1 is equal to K2. Okay, so if EK1 is equal to EK2, how can we use that? Post compose it with F and G individually. So what can you say about EK1 F? This is FE K1 and this is equal to GE K1, which is GEK1. Okay. Similarly, if I replace K1 by K2, I will get the same identities. So therefore, there are two different ways in which, like, can you see that EK1 equal to AK2 by choosing EK1 equal to EK2 equal to H? Yeah. So choosing, and similarly for K2. So choosing H equal to EK1 equal to EK2, we get a unique factorization of H through E. i.e., in other words, what can we say? That K1 is equal to K2. So, I mean, let me go back to the picture. I'm scrolling up. So, choose this H equal to EK1 and EK2. Then there are two different factorizations. I can choose D to E to be K1 or I can choose it to be K2. But because we know there exists a unique K, so therefore uniqueness forces K1 to be equal to K2. So therefore what we have shown that if EE is an equalizer, then E is a monomorphism. In general, there is a definition for all such monomorphisms. So a morphism E from C to D is said to be a regular monomorphism if there is a pair D to D prime such that pair of morphisms such that E is the equalizer of F and G. Yeah, so regular monomorphisms are precisely those monomorphisms which occur in this particular fashion. So what we have shown, all split monos are monos, or regular monos are monos. But in general, can we show that all monos are regular monos? Well, that is true in the category of sets. Yeah, because in category of sets, everything is correct. So maybe I can give you this as an exercise. Yeah, so in sets, regular mono, if and only if mono. Okay, then dually we have the notions of co-equalizers. Yeah, all the arrows are reversed. And we have the notion of regular epimorphism.
Is there a relationship between regular mono and split
Regular mono
mono?
and split mono, no. Yeah, these are defined independently. But oh yeah, I think split monos can be treated as regular monos. Split monos are regular monos. Because if you have a splitting, suppose E is a split mono, then there is some E prime which works. Yeah, so okay, I will just write it as a property. Split monos are regular. So suppose you are given this, so C, D, that is E, and you have E prime. This is clearly a surjection. This is an epimorphism. The splitting is an epimorphism. So then you can take two different maps, yeah, from D to D. One is identity D, and the second one is this composition E prime. So E will be the equalizer of these two arrows. And this is actually, you made me prove that all in the category of sets, regular monos are precisely monos, because monos are precisely split monos. Right? Okay. So regular epis are precisely surjective functions in sets. If you remember, we said that split epis and surjective functions, they don't have this relationship unless you assume the axiom of choice. But regular epis and surjections, they are precisely the same. And this is a good exercise for you to understand the dual concept of regular epimorphisms and work with them in this category. And similarly, in the category of groups also the same thing will happen. Yeah. However, in this part, the second part is also true. I mean, maybe this is second example by now. Let me go back up. This is the first one, then third one. So in rings, we found some epimorphisms which were not surjective maps. Yeah, the localization maps. So Z to Q in particular. However, regular monomorphisms are more natural. So regular epi if and only if surjection. Try to see if you can prove these things. Then in the category of topological spaces, what are regular monomorphisms? So regular monomorphism is inclusions of up to isomorphism, okay, up to iso, inclusions of subspaces. These are regular monomorphisms. Inclusion of subspaces, you understand that the topology is precisely the restriction of the topology on the bigger set. And regular epimorphisms, this is also quotient maps. So quotient topology, if you know, then these are precisely the quotient maps. You understand this? So these are all exercises. Yeah, I have just written them down, but you have to verify. So like the story is so far is that we saw what is a terminal object, initial object, equalizers, co-equalizers. They all look very different, but the underlying properties are exactly similar. We are asking for some universal property, we are asking for some best possible solution, which for a given problem. The given problem is going to be some sort of commutative diagram, and we are asking for a best possible solution. Now, can we generalize all these things to a common ground? And the answer to that is yes. They are called categorical properties, or in particular what we are talking about are called limits and colimits. Yeah, so limits and colimits are extremely important things in category theory. And in order to understand limits and colimits, we need to go through some other exercise. We want to construct some new kind of categories from existing categories. So I'm going to give you two different ways. So constructing new categories from old ones. Sometimes you are working in a category and you want to understand only the fraction of that category, only the part that is visible by placing visible from a particular location. Like you placed an observer in that category at an object, and then you want to see what kind of things you can see. Okay, so that's called a slice category. You are looking for a slice of your original category. So first one is slice category. This is perhaps the most simple thing. So C is a category and C is an object out of C. The slice category has, so objects of the slice C, C by C, yeah, are morphisms, are pairs. Maybe I should write them as pairs. Pairs A comma F, where F is a morphism from A to C. And what are morphisms? Morphisms in the slice category, they are defined between, yeah, these are commutative diagrams. Okay, so in particular I have to be specific, like if I'm talking about AF and then I'm talking about BG, then this the morphism is H, such that H will make the diagram commute. So let me write that. So this is F, okay, then I'm talking about B. So B to C there is a morphism G, and H is a morphism from A to B which makes the diagram commute. Yeah, such that GH is equal to F. Can you see why we are talking about a slice? Yeah, that we are placing an observer at a particular object capital C, and then we are only looking at what's coming to you, the incoming traffic, and then all the ways in which you can connect those two, that's called a morphism. Yeah, not all morphisms from A to B are going to be morphisms in this slice category. You have to satisfy this commutativity condition. In particular, like this is not something very awkward, okay? So note that if T is a terminal object in C, then the slice category C mod T is isomorphic to C. Why is it isomorphic? Because what is going to be F? A comma F, what is going to be F? F is the unique map. So the commutativity condition is always true. It doesn't matter. Yeah, so it's as if it's non-existent. So therefore you are just getting back your original category up to isomorphism. So yeah, if there is a terminal object, then the collection of all slices, if you have some property for all slices, then you also have a the same property for the category itself. Understood?
So it is true for all ABC, or something is fixed?
What is true for all ABC?
That means you take first object C,
Uh-huh.
and depending on object you get A and F.
Object C is fixed. If you see the in the objects for this category, slice category, we are just writing A comma F. Yeah, we are not explicitly mentioning C because C is fixed in the background. Yeah, even though F is a morphism with target C always. Yeah, but if you change the slice, then you will get different things. If you take a two-element set, for example, in the category of sets as your C, then what is it? No, two-element set is perhaps not a good choice. Like a co-slice with terminal. Yeah, co-slice category. Co-slice category, I'm just going to write it like C mod C. Yeah, it's written this way, and these are all arrows going away from that, and all morphisms which make this diagram commutative. Yeah, you simply change all the arrows. Direction of G is also going out. This one doesn't have to change. No, H is like, I'm saying that H is a morphism from A comma F to B comma G. Yeah, perhaps I have changed the ordering of like labeling of A and B. Yeah, when I dualized the diagram. So this is a co-slice category. If I is an initial object, then the co-slice at I is again going to be isomorphic to the original category. But if you take all these singletons, then what's really happening? Like if C happens to be a singleton set, terminal object, then an arrow is an element. Yeah, it's a set together with, like, an object of the co-slice category is a set together with an element. Yeah, so it's a pointed set, and then you have to you are recovering that the category of pointed sets from this. Yeah, so if I is initial, then the co-slice is isomorphic to C. If T is terminal, yeah, let me just say the co-slice at terminal in sets is isomorphic to the category of pointed sets and point preserving functions. You understand this? Now that's all the requirement we have. So you can see that we can create lot of things just by doing this. Just taking slices and co-slices. Now let us take this up one notch and define something called an arrow category. In literature for category theory, there is also another name for category of arrows. Yeah, we are not talking about that. We are just talking about the arrow category here. And we are going to do the slice version of that first. So let F be a functor and B is a fixed object of D. Then we define the arrow category F arrow B. Okay. What are the objects? Objects are A comma F, where A is an object in C and F is a morphism from FA to B. And what are morphisms? So from AF to A prime F prime, the morphisms are those H's where H is a morphism from A to A prime in category C, such that this triangle commutes. What is the triangle? We have FA to B, we have FA prime to B prime to B. This is F prime, this is F, and this is, what is this arrow? FH. Yeah, this is FH, such that this commutes. So we are trying to encode lot of data here. Yeah, we are fixing an object in the target category and we are taking objects which are pairs. Yeah, you will take some time to understand what's really going on here. But you can imagine that perhaps there is some similarity between our original slice category and arrow category. Can you recover a slice category as an arrow category? Identity functor, very good. Identity functor. So the slice category C mod C is nothing but sorry, I should draw an arrow, 1 sub C arrow C. Dually, can you define the other arrow categories? Yeah, where the object is fixed in this source category. Is it true? Is that the dual? Object is fixed in the source category. Will that work at all? We should take op of what? Yes, exactly. That's my question. Like sometimes people think that taking the dual version is very easy. Yeah, it's not that straightforward. If you know this logic that slice is nothing but 1C arrow C, then co-slice is going to be C arrow 1C. But what exactly are we doing? D-op. No, D-op is not really the right thing. The arrow, the opposite, the dual version is this. The other arrow category is simply B arrow F. Okay. You are just taking, I mean, I will just draw the commutative diagram so that you can understand. So this is F, this is F prime, and this is FH. This diagram commutes. There are generalizations of this also. Yeah, I mean, in both components you can take functors. So there is a pair of functors mapping into the same category, same target category. There is C, D and E to D. There are two functors and you can play the same game. Yeah. In category theory, everything has a generalization. So, but so far we will only need these. Yeah, in the slice category, arrow category, and their dual versions. Is this clear? This idea? Okay. So now we are ready to define limits. And colimits. Okay, so limit is always assigned to a diagram. Yeah? And that diagram has a shape. Usually the shape is small, but there is a shape. So let J be a shape category. Yeah, there is no definition, but I'm just going to say usually small category. There will be only one instance when we will have to relax this condition. Yeah, so J is a small category, and we call it the shape category. J is any small category.
What does shape category mean?
No, so this is the shape of that limit. We are going to talk about that. Yeah, so for example, this is a shape. There are two arrows between two parallel arrows between two objects. This is a shape. Yeah. Then there is also just this, a shape. I'm not even labeling them. Yeah. Then maybe this is a shape. Any small category would do. Every small category is a shape. Okay. So let a functor, a functor from, we are going to call it D, from J to C is called a diagram of shape J. So basically, when I take this first shape, let's say this parallel arrows, when I map, like take a functor from this shape to a category, then I am replacing those objects with objects of C, and I am replacing the morphisms by morphisms between those objects of C. So that's a diagram. Okay, so this is a diagram of shape J. And we are trying to understand something. Yeah. Now there could be two different diagrams. I mean, give me some simple example of a diagram. Let's see if you can construct. If you know one object exists in category C, can you give me some example of a diagram? Function to itself from what to what? No, you have to be more specific. So for any C in objects of C, there is a diagram. What does that diagram do? I'm going to say delta. Yeah, this is a diagram, delta of C from J to C, that takes, what does that do? That takes, yes, every object little j of J to C, and every morphism J to J prime in J to identity of C. We always have this diagram. I have written delta because it's the constant diagram. Yeah, constant diagram of value J. With value C. Okay, now because we are doing category theory, do we really stop when we have a map from objects to objects? We should do morphisms to morphisms. So now if we have a morphism from C to C prime, then we have a corresponding morphism from delta C to delta C prime. Yeah, the construction delta is functorial in C. Yeah, basically, so i.e. delta is a functor from C to the category of functors from J to C. So what happened? I mean, if this is my shape, yeah, I mean, I'll give you an example. If this is my shape, yeah, the green one, highlighted green one, then what was the original diagram? So we had C to C prime in C. Let me call this F. Then what was delta C and delta C prime? Well, delta C is just going to be C and a pair of arrows, 1C, 1C, and this is this 1C, 1C, C prime to C prime. And what do we need? We have a pair of morphisms FF such that this outer triangle commutes, outer rectangle commutes, this one. And similarly, the inner rectangle also commutes. Both of them will commute. That is precisely what we mean by it being a functor. So what we are saying is that delta, so let me go back. So what I am saying is delta of F is a natural transformation from delta C to delta C prime, because we have seen this is the functor category JC. The objects there are functors. Those functors are called diagrams, and the morphisms there are natural transformations. So this is a natural transformation. Delta F is a natural transformation from delta C to delta C prime. Do you agree with that? If you remember what is the definition of natural transformation, then for this particular shape, you require that these two purple squares or rectangles, they commute. That's the only condition. Some of you are lost. If you have any questions, tell me. Because there are two parallel arrows. What do we say? What do we say for a natural transformation? For every object in the original diagram, there should be one arrow. Yes, so that arrow is the vertical one, such that for FF and GF, they have to agree. Yes, so this first identity is FF, the second, and then this is FG, and this is GF and GG. There are different things happening here. Try to put everything together. Yeah? Okay, so therefore delta F is indeed a natural transformation from delta C to delta C prime. Okay, now we are at the right setup. We have got one category, one functor, and we want to talk about one particular object. See, what did we start with? Originally we were given a functor D from J to C. Correct? A functor was given. Now we have found, like this functor is an object of the target category of delta. Okay, and we are given a functor with this target category. So now we have the correct setup for the arrow category. And what will be that arrow category? Delta arrow D. Okay, so consider the arrow category delta arrow D. Okay, what are the objects? Let's just revise. The objects are, you are supposed to start with pairs. Objects are pairs, right? You have to choose something from C in object of C, and some morphism, right? Some morphism from its image so delta C to D. Okay, and this is what we call theta. Yeah, theta is a natural transformation from delta C to D. Okay, now let me try to draw this diagram. I am going to for this particular picture, okay, we have J1 and J2, two objects, and let me call this one alpha and this one beta. This is our J. What is going to be delta C? Delta C will be C, C, identity, identity. Then at the bottom, what do I have? It's dj1 and dj2. This is my actual diagram. Yeah, this is d alpha and this is my d beta. D alpha, d beta. And then I need a natural transformation. So natural transformation is given by these vertical maps. The first one is theta j1 and the second arrow is theta j2, such that this whole thing commutes. Yeah, commutes means what? That theta j2 composed with the upper identity is equal to d alpha composed with theta j1, and theta j2 composed with lower identity is equal to d beta composed with theta j1. Yes, both those squares should commute appropriately. However, this situation, yeah, I mean, you can see there is this top layer of this particular diagram. That top layer has got some redundant information. Everywhere we are just talking about C, C and 1C, 1C, identity of C. So it has got lot of redundant information. So just like in topology, I mean, if you think of this as a filled up square, yeah, I mean, this is a filled up rectangle. And in topology, if the top two corners of that, they are exactly the same, then you might want to pinch them into a single point. So actually that is also possible here. See, I am going to convert this diagram into something like this. I don't really care about identity. I just care about one object and this. So theta j1, theta j2. So just like in topology, we call this a cone over the diagram. Okay, so this is, and so objects are this, i.e. cones over diagram D with summit C. I mean, this is a cone, sorry, i.e. a cone over diagram D with summit C. Summit is the topmost vertex. That is what we are choosing. Yeah, so you can see we started with some very complicated thing. Yeah, what was that complicated thing? An object of an arrow category. But what we are really doing, we are just taking a cone over this diagram. If I had said cone, you would have understood. Yeah, you are taking a diagram, base diagram, and what should be satisfied here? Well, we are saying that d alpha composed with theta j1 is equal to d beta composed with theta j1 is equal to theta j2. That's all we are saying. Now, okay, these are the objects, and what are going to be the morphisms? Well, morphisms are morphisms from C to C prime. such that this whole thing happens. So let me scroll it down. So the morphisms here are morphisms in C. Let me call it F, C to C prime, such that the cones commute. Yeah, I mean, let me just write it in terms of cones. Yeah, that for C you have got this outside thing. This is dj1, this is dj2, and we have got d alpha, d beta. And for C prime also I have got a similar situation. I will just call this theta prime j1, this is theta prime j2, this is theta j1, this is theta j2, and the morphism here is just F, and this F makes these two triangles commute. If you write everything properly, then this is what you will get. Yeah, in this arrow category, such that this diagram, such that the following diagram commutes. Okay, so these corner triangles, these are the important ones. They commute. Okay, now any questions so far? Look at this. Yeah, I'm taking your attention to just this part. D alpha theta j1 is equal to d beta theta j1. Yeah, theta j2 is the connecting piece of information for these two. How can I obtain theta j2? Like, theta j2 is a redundant leg of this diagram. Okay, so in this diagram, this is just some piece of notation. This is the summit and this is a legs of the cone, and this is a redundant leg. Because theta j2 I can already obtain by composing d alpha with theta j1, or equivalently d beta with theta j2. I don't j1. I don't need to talk about explicitly the leg theta j2. So what is really a cone over this diagram? If I remove the redundancy, then a cone is simply this. Yeah, after removing redundancy, what do I get? I just get this. D alpha, D beta. This is a pair of parallel morphisms in the original diagram, and I have theta j1 over here. Is this diagram familiar to you? Equalizer. But equalizer would be the universal such thing. Right? We haven't yet asked for that. Okay, so now I am ready to define what is the limit. Say that a limit of diagram D from J to C exists if the arrow category delta arrow D has a terminal object. Okay, so this, and we write limit of D of shape J equal to C comma theta J, J in object of J, this data. Okay, where this is the, yeah, where RHS is the terminal object. So what is a terminal object? It is simply one object of category C together with, I mean, that is the summit of that cone. So the limit cone has one object and legs. Okay, so basically the limit cone here would be, I mean, if you want, I can call it, let's say, C bar instead of C. The limit cone in this diagram would be this, C bar to dj. Okay, maybe we can also call it theta bar j. So theta bar j1, such that there is a unique arrow. Why does there exist a unique arrow? Because it's a terminal. Amongst all such objects, amongst all such cones, it is the terminal cone. Okay, so that's the definition of a limit. Now it's very abstract. Yeah, we started with a shape, then we took the diagram, but actually it's not that hard. It's just difficult to express it in categorical language. It's a terminal object of some category. Now what is that category? You have to understand. And the idea, as you can see, like MacLean and Eilenberg, who started this subject, who wrote down the axioms of category theory, they were topologists. So you can see the idea of cone being used. A commutative square is like a cylinder, and then you are pinching one side, that's a cone. Yeah? So very beautiful idea, like it looks very complicated, but it's very simple relatively. Yeah? The actual idea is very simple. Okay, so there is some more terminology naturally, and that is of dual. Dually, we have a cone under a diagram D. What will that be? Cone under a diagram? It will be an object of the other arrow category. Yeah, i.e. an object of the arrow category D arrow delta, and we say that the colimit, that a colimit, yeah, I shouldn't even talk about a colimit of D exists if this arrow category has an initial object. Okay, so that initial object is going to be the colimit. Now I'm sure most of you are confused about this bunch of notation, but let's do something simple. Yeah.
So
Yeah.
are there corresponding notions of being initial in the other arrow category or being terminal in the latter arrow category?
No, we don't use them. We don't need to. Yeah, we only need the terminal cone over a diagram, and we need an initial cone under a diagram. If they exist, then only they matter. Yeah, otherwise they don't. We want the best possible solution for a certain problem. I'm just going to show you some examples and then we will proceed with some general theory. So let's do some examples. So take the shape to be empty. Let J be the empty category. Perhaps this is not the simplest possible example. If J is the empty category, then what happens? What is a diagram? In a diagram, nothing happens. Yeah, J to C, that's a diagram. So, so that D is empty. The diagram itself is empty. Okay, so what will be delta arrow D? Then delta arrow D has as objects just C, comma nothing, no morphism. Yeah, it's just an object of our original category. And morphisms are just morphisms of the original category. There are no conditions to be satisfied, no triangle to be satisfied. So therefore, a terminal object, yeah, I should say delta arrow D in this case is isomorphic to C. Yeah, nothing else is happening. Isomorphism of categories. And therefore, limit of shape J is a terminal object. Of C. Okay, so it's just a terminal. Nothing more, nothing less. Let's increase the complexity a bit. Let J be a single object discrete category. Okay, what is a diagram in this case? D from J to C. It's a single object discrete category, only arrow is identity. So what's a diagram? Identity goes to identity, so you are just choosing one particular object. That's all. So it's one object. So that a diagram is D is a single object. Okay, so now you are given a single object. Let me call that object A. Now what is going to be a cone over this diagram? Cone is simply a choice of object with a morphism. Correct? A cone is a choice of object of C together with a single morphism. This is the C is the summit and this morphism is the leg of this cone. Yeah, this is summit and this is leg. And now I am asking you this question: does there exist a terminal cone like this through which every other cone factors? What? Yes. Yeah. So the limit of this diagram, so this, let's say this is this diagram is A comma identity A. Okay, you are simply recovering. Yeah, let me write this. So A is with identity A. There always exists a unique arrow. What is that unique arrow? Namely F itself, such that this diagram commutes. Okay. So these examples will at least convince you that the idea of limit is not that hard. What will be the colimit of this diagram? It's again the same thing, A comma identity. Yeah, it's a cone under a diagram, but again you have to factor through A comma identity. In case 1, what was the name of the colimit of empty shape? It is the initial object. Okay, it's the initial object of the original category C itself, because it's a cone under the diagram. Okay, so let's do a slightly complicated example. So J is J1 and J2, just two objects. Now what is a cone over this diagram? How many legs will it have? As many objects. Yes, so I'm not going to write anything. A diagram is just going to be A comma B. A cone over this is just going to be a pair of morphisms. I'm just going to call them F and G. And what will be the universal cone? If A and B are sets, then does there exist something here, yeah, together with some arrows, such that there always exists a unique factorization? Is there a universal object satisfying this property? A intersection B? No, we are not talking about inclusion here. Intersection is not correct. Cartesian product with projection maps. Okay, so let me write that. So here we are talking about A cross B. Here we are talking about sets and pi 1 and pi 2. What is the map from C to A cross B? The factorization, unique factorization which makes this work. What is that map? F comma G. In the first component it just maps to F. That's the only thing you can do. In the second component it maps to G. And now if you check, then F comma G composed with pi 1 will give you F, and F comma G composed with pi 2 will give you G. So limit of this shape is called a product with projection maps. Yeah, so projection maps are important. I mean, that object together with this pair of projection maps, that is what our product is. Generally in set theory, because set theory is all about the internal structure, so we forget about the maps conveniently. Yeah, but products cannot exist without projection maps. Yeah, so product is actually this tuple. Okay, one before we go any further, I should say that the limit of a diagram if exists is unique up to unique isomorphism. Can you understand why? Because a limit is a terminal object in some category. So that's always unique up to unique isomorphism. Similarly, I mean, colimit also. Yeah. Okay, so therefore, now I can talk about, like, I wanted to say this because then I can say the product is A cross B, comma pi 1, comma pi 2. This is our common notation. Yeah. A cross B is the notation. Now, whether it is actually Cartesian product or not in a given category, that's irrelevant. The notation is always this. Now, dually, yeah, dually initial object, then dually just A comma 1A. This doesn't really change. Like this second example is actually boring. Yeah, nothing is happening there. You just factor through identity. And dually, this is called a co-product. And we write A plus B with co-projections, nu1 and nu2. Yeah, these are called co-projections. Just for your help, I'm going to draw this diagram of co-projections. Like we are given A and B, and then A plus B, and this is my nu1, this is my nu2, and finally I have some other cone under the diagram. Some people also call it a co-cone. Yeah, but we are not. Huh? No. Cone and no. No. That's not fair. And the morphism here, yeah, if these are morphisms F and G, then we call it, sorry, we usually write them vertically. Yeah. F and G. So you can think of it as the sum map. You are choosing one entry from A and another entry from B, and then whatever their images in C are, then you are taking their sum. Okay, so products are of this kind. Now, instead of talking about general shapes, let's do another example. Now, if, I mean, this is the same example. If P is a poset and yeah, thought of as a category, then product of two elements A and B is what? The so-called meet. Is their meet, and it is written A meet B. The dual version is the co-product, and it's called join. Now let me give you the diagram for this. A, B, and then A meet B, and then there is some C. What is the meaning of arrows? Arrows means in a poset, what are arrows? Less equal signs, right? So what we are saying, now read the universal property. Universal property says that whenever C is less equal A and C is less equal B, then C is less equal A meet B. Right? So if you are thinking about the power set of a set, then meet is just going to be the intersection. in this case, actually less equal signs exist, that much is sufficient. Yeah, you don't really need these maps. Maps are just less equal. So you will say that the product is nothing but just that element. It's enough to talk about that element. Similarly, coproduct is the join. In the power set, it will be the union. Yeah? So if in particular, now this is me answering your question earlier. At the beginning of the course, we started with a question. If we are talking about natural numbers without zero, with zero is also allowed, and divisibility. So in divisibility poset, this is a poset, and in this there will be products for any pair. The products are GCD. Something divides something, something divides something, then it must divide the GCD of both of them. And coproducts are, yes, this particular poset, like for any foundation is person, natural numbers always contain 0. So 1 is the initial object. 1 divides everything and everything divides 0. Yeah, so I'm saying 1 is the initial object, and 0 is the terminal object. I'll make just one comment. If you do not want to get confused between limits and colimits, always make sure all your arrows point more or less downwards. Limits are always cones over the diagram and they are closest to the diagram, and colimits are always cones under the diagram and they are closest to the diagram. If you change the order, you will get confused. Okay. One last thing, we say that, yeah, I mean this is a part of now theory, say that a category C has limits of shape J if for each diagram D from J to C, the limit of D exists. Okay, dually you can write down about colimits, that C has colimits of shape J if for each diagram the colimit of D exists. See, by changing the diagram, I mean, for example, in a poset, by changing the diagram, I mean changing the elements. It can happen that in a certain poset, a particular pair of elements has a meet, but there is another pair which doesn't have a meet. They don't even have a common lower bound. Yeah, that's always a possibility, right? So therefore, you have to understand the difference between existence of limit for a particular diagram and existence of limit for all diagrams of that particular shape. Let's stop.